So in the previous segment there were some slight typos. Here I think I had written 2 in place of 3, here also I had written 2 in place of 3. So these things should be corrected, and yeah. So the observation which you should have from this is, by putting some values, in fact you should try to write a code just to plot this, nothing else, for different values of rho 1 C1s, okay, at a different layers and at different lengths of the middle layer at different frequencies. So there are so many variables, right? 5 variables which you have now, 3 properties and 1 geometric parameter and 1 frequency parameter. So based on all these 5 things, you will see different sound pressure, sound power loss in transmission. Okay. So if you write a code and play around with some values, then you will see the trend. You can get some feeling about that. Okay, please do that. And now what we will do is we will take up this thing and try to see some special cases, because this has got this 3-layer thing has got lot of special cases which are of importance. So that we will take up in this segment. First being the case where you have rho 1 C1 is equal to rho 3 C3. That means on both the sides the medium is same, and you have, that means you have inserted something in a particular media. For example, there are 2 rooms and you have now put something in between. So that's the condition. And one more condition we will put is rho 2 C2 is very very high as compared to any of them. Okay. So that's the condition. Plus we will put another condition, third condition, that K2L is such that okay, this is approximately equal to, I can write like this, okay, K2L is small. Now so you know, here when we say a single parameter being small, we are talking about 2 things. As I said, it has got 1 geometric parameter, 1 frequency. Now whenever you say the words like small, big, far, near, as in the context of sound or light, you should also mention one of them, otherwise it doesn't mean anything, because your small and big will be decided based on what frequency you are talking about. Because see here, this K2 will have this, so this basically is L over lambda, right? This is K is 2 pi over lambda. So you are talking in terms of this L over lambda of the frequency of interest. Now when I am saying K2 small, either the length, physical length of the in between layer could be small for a moderately high frequency, or length is more but you are considering a very small frequency, so that lambda is very high. As you said, no, it took 100 hertz. In 100 hertz lambda is very huge, right? And so as compared to how much is lambda for 100 hertz? Almost like 3.5 meters, right? Now in comparison to 3.5 meters, if you take even L to be say 10 centimeters, it's small, okay? But if you go to say 1000 hertz, 10 centimeter becomes comparable with 30 centimeters, and you go to 10,000 hertz, it becomes 3 centimeters, then everything changes. Everything changes, because then your whole system, in fact inside that a second layer, variations of pressure can be seen. But at 100 hertz, the whole system acts like a single object. You see that? So that's one very important concept. At 100 hertz, when the wavelength was say 3.5 meters, and suppose this is 10 centimeters, okay, 1 feet wall even, okay, even 12 inches. So as compared to that, it's small. So if you try to visualize the wavelength, it will be like, you know, like this. So no appreciable change in pressure or particle velocity is observed in that. So that's where you can consider this whole thing as a single object. For that wave, the variation is not very significant, so whole thing is like a single body moving. So there the term lumped analysis you might have heard, no? Lumped parameter analysis. In thermal science also you always do that. If depending on your thermal conductivity and all those things, a body can be considered lumped or a distributed. So here the same thing, okay. So at what frequency you are talking about, so that will decide whether you can consider a lump. As I was saying, if you go to 10,000 hertz, so your wavelength will be so small that inside that pressure will vary like this. So then the same wall is now considering, behaving as a distributed element. Pressure is varying inside that. So that is how you should always be very careful about using the adjectives like small and big and far and near. Okay, you should always talk in terms of, and you should keep in mind that K2L is that non-dimensional quantity sort of, which is giving you the idea of smallness as a whole. Okay. So now these are the three conditions if you apply. So the alpha t which you had derived in the earlier segment, so now that can be written as, what was the form that I had written there? This, and in fact this if you expand, okay, if you put this and expand it, I'll write that expression for, so that, where is it? Yeah, I'll write that first and then, so this will come out to be rho 3, sorry, C3 rho 1 C1 over rho 3 C3 plus rho 1 C1 squared cosine of K2L plus rho 2 C2 plus rho 3 C3 rho 1 C1 over rho 2 C2 square sine squared of K2L. So this is the expression which you would get, and now you apply these conditions. So rho 1 C1 is equal to rho 3 C3, and then this term will become K2L, and then again rho 2 C2 is very as compared to rho 1 C1 it is large. Okay. If you do that, so what you will get is all those simplification. So I'll put the final approximation as here it is approximate. Okay, it will come out to be 4 rho C1 square over rho 2 square C2 square K2 square L2 square. Okay, so this is C. So this is what you will get under these three assumptions from this expression. Fine. Now, if you, so there is one important observation which you can make from this. if you remember in the last to last segment, we had derived an expression, not for this, say a tube was there and then we put something, spring, damper, like that, you know. So with Zn being its impedance. Now, and there we had derived an expression of alpha t, the we called it power absorption coefficient or power transmission coefficient. We came to that from a two-layer transfer thing and transmission of wave, and then we replace that, saying that if it is a solid, then we can replace this with an impedance, equivalent impedance, and the alpha t was 4 Rn rho 1 C1 over Rn plus rho 1 C1 square plus Xn squared, where Zn was Rn plus j Xn, right. Now, this one, the same expression you can get if you think of an equivalence, that just an additional mass term if you put, that means, see, if I replace Zn with rho 1 C1 plus j times, it will be, say, I will write in terms of omega maybe, omega rho 2L. If I just substitute this here, I will get exactly the same as an approximation, which we got 4 rho 1 square C1 square over K2 square C2 square rho 2 square L square. Is that the thing which we get? Yeah. So this is what you will get if you substitute Zn as this in this expression. Now, what does it tell you? It tells you that if these three conditions satisfy, that means what? There is a very light fluid which you are talking about, like air. Suppose this is like air, and you have put a thin sheet of material. It need not be liquid, because you remember we told that this rho c thing you can calculate by using that b plus 4 by 3 g under root rho or square root. That velocity you can use and consider that to be a fluid, and then you can use that solid wall. Now, so that means a thin wall, if you put in air medium, it is just like adding a mass and nothing else. You see this one, and this side, it is the rho 1 C1 again is the radiation impedance, or not radiation, the characteristic impedance of the air medium, that side. So that takes care of the resistive part. So the reactive part is just one more mass term. There is no stiffness kind of term, right? 1 over omega you are not requiring. If you add j times omega rho to L, you are done. And what this rho to L is, it is so this one, generally this rho to L, you know, it is expressed as even sigma, and that is nothing but your surface density of the material which you are using. Suppose this is in kg per meter cube. You multiply with the length, you will get kg per meter square of the same thing, right? So that means the length also has been taken into account if you use sigma, and so of that mass, so it is giving you just j omega times m sort of expression. So it's like you are just adding an additional mass type of impedance, nothing else. Okay. So this thin, when I am using, again the same thing, that means the frequency is such that the length can be considered as thin. So that is why the whole thing is just moving like a single mass. Stiffness is not at all coming into picture. It is the wave which is impinging on this is trying to push it like a single mass. Okay. And the everything that again this layer of material is trying to push the other side air with this impedance which is completely resistive. So that's how it behaves, and you get the same expression. And finally, this is generally written in this form. Because rho 1 C1 over, so this omega you can split with this k is 2 pi f over c, so those things will cancel out and you will get something like this over sigma square f square. Okay, this is the general form which is written. And even generally for air, suppose you calculate this thing, they are constants, and just you can write like some number, I think it was 42 something, minus 42.4 plus if you consider in dB, so not here, I'll write that not here. So this is your this is your coefficient. You can write that in terms of dB, that loss, transmission loss. So that so if I write that, so transmission loss will be equal to minus 42.4 plus 20 log of, because this log of sigma f. Okay, so this expression only in dB, and because this is the constant, you just have evaluated it. This is for air. Okay, it means if you put a thin material in air, the transmission loss will be given by this. Now if I ask you that if I increase the thickness of the layer by double, if I double the thickness, how many dB reduction or how many dB transmission loss will be increased? So log 2 is almost like 0.3, so 6 dB. That 6 dB reduction is always you keep in mind, because log of 2 is 0.3, so and 20 times that is 6. So that means if you increase the thickness, and thickness is coming here, right, inside this sigma, the thickness is sitting. So if you increase the thickness of the layer by 2 times, you will get a 6 dB reduction, which is perceivable. Or else you can do what? The same expression, if you are considering the frequency which is twice. Then suppose you got a transmission loss of say 40 dB for 500 hertz. If I ask you now for the same wall, what is the transmission loss at say 1000 hertz? Just what did I use? What was the transmission loss I took example? 40 dB. If it was 40, then it will become 46 dB. Right? Because you just increase the frequency by 2 times. So again the same thing. So are you seeing that? It means they are the same, means two sides of a same coin type. The increase of frequency or increase of length, they are behaving in a same way. Okay, one sitting inside sigma, one sitting inside the frequency f. Okay, and some for some general values, if you listed in the book, if you take a brick wall of say 12-inch thick brick wall at 500 hertz, you get 53 dB reduction. Okay, because the density is such, like, okay, and concrete wall 4-inch thick at 500 hertz will give you 45 dB reduction. So all those things you can simply calculate from here if you just know what the surface density kg per meter square of any material. So that's how you can calculate. But there is a restriction or limitation of using this. We have evaluated all this thing by considering normal incidence, right? Wave is always hitting the wall normally, head on. So, but in general waves will come at various angles, so a random incidence it is called. So for that a thumb rule or a experimentally evaluated empirical formula can be used, which is like this: minus 17 plus 15 log of sigma f, but this one is for sigma in pounds per feet square. Okay, this sigma you have to be careful. You can convert this if you want for kg per meter square. You just use the conversion factor here, take that 15 times log that you take out, you can get in kg per meter square also. Fine. Okay, so that's about the application of one of the special cases we took of this 3-layer system, and we will discuss the other. There are, I think, other 3 or 4 special cases needs to be discussed, and we will take up them in the next segment.